Hey everyone. So in this last video, we are going to look at one last example that is a combination of both talking about normal distributions and binomial distribution. And after we go over this problem, I'm going to go back and visit a previous problem. And I just want to show you how z-scores play into all of this and the historical way that people would find it. And some people still use this method today to find the answers to some of these questions. Okay, so the amount of money spent on a first date is normally distributed with a mean of $1,200 and a standard deviation of $30. Sorry for that typo. If I take a sample of 200 first dates on average, how many of those 200 first dates paid over $105? All right. So first, we want to know on average how many of these dates paid over a certain amount. And so we need to know the probability of paying over $105. So that first part, the probability of paying over $105, I'm going to use my norm.dist function for. And I know that this is the same as finding 1 minus the probability that x is less than 105. And that is just a straight norm.dist. We're going to find a norm.dist. Let's actually spell it out before we do this. We have our x value. We have our mu. We have our sigma. And those are 105. I'm sorry. This is another typo here. It's $120, not $1,200. These people aren't crazy. So $120 is the mean, and then the standard deviation is $30. All right. Can you imagine spending $1,200 on a first date? Can't really imagine that. All right. So we're going to do norm.dist. We're going to find, we have x, we have the mean, we have the standard deviation, we have true because it's cumulative, and we get 0.30. Oop, I forgot to do the 1 minus. Sorry about that. 1 minus gives me 0.6915. Okay. I knew something didn't seem right there. So we have 1 minus the normal distribution because it's 1 minus the probability here. So this right here is the p in the next part of this problem. So the probability of success, which in this case, the probability of success is going to be, that somebody paid over $105. So we want to know how many people out of 200 would pay over $105. And so we have our P, we have our N is 200, and we know that mu is equal to NP. So in this case, it's going to be equal to N times P, and we get 138.3. So we would expect about 138 first dates to have spent over $105. All right, so I wanted to go back and look at this previous example about systolic blood pressure. And we know that we were finding the probability that your blood pressure is between 115 and 125. So if I found the z-score for the larger z-score, and I found the z-score for the smaller z-score, so the way I do that is we know that the first one was 125, so we're going to do 125, actually we have the value right here, minus the mean. So I'm going to subtract the mean, and then I'm going to divide by the standard deviation. And so if I do the same thing for the smaller z-score, I get this value here, and now I'm drawing from these numbers over here. And so you can see the z-score for the larger number is 0.25, and the z-score for the smaller one is negative 0.25. And so before we had calculators and computers and Excel to do all of this work, people would use tables. And so here's a table right here that gives us the different probabilities under, so the area under the curve below a certain value z for a z-score. So what people would do is, instead of having to find the probabilities for each individual normal curve, they would standardize their scores and then look at this one curve, the standard normal curve. And this table gives us all the probabilities from negative 3.49 all the way up to positive 3.49. Okay? And so in this case, what we would do is first we would find the area under the curve for this first z-score. Where'd that guy go? There it is. So we have the larger z-score is 0.25. And so what you can see here is at 0.2 here, I want to write, I guess I'm highlighting. At 0.2 is the first decimal, and then 5 is the second one. So that's here. So we're going to look at 0.25, which is this value right here. And we get that the area under the curve here was, what was that, 0.5987? So 0.5987. Now that's the area all the way below that value. And then if we look at the area under the curve below negative 0.25, which is up here, so here's negative 0.2, and then 0.5 is here, so we're going to follow that down, and we get 0.4301. Is that what it was? Man, I forget as soon as, oh, 0.4013, had the right digits, 0.4013, okay? And so what we would do is we would take the larger area and subtract the smaller area from it, and we'd get the area between the two things. And notice how this number comes out to be the same as this number here. So we don't have to deal with z-scores anymore in that sense, but we will be using z-tables probably in the future for other topics. So I just wanted to show you a little bit of that history of how why we use z-scores and why they're still important, because some people still calculate probabilities this way. All right, see you in the next one.